This final chapter organizes the book around three empirical goals, reviews least squares assumptions and estimators, provides a glossary and formula cards, diagnoses common mistakes, connects regression with machine learning, and closes with a review of nonparametric regression. The most important organizing decision comes before any calculation. Are we describing, predicting, or estimating a causal effect? Description asks what the data show. Prediction asks how well we forecast new outcomes. Causal analysis asks what would change under an intervention. The same regression output can appear in all three, but the methods, assumptions, and interpretation differ. Confusing prediction with causation is one of the most common errors in applied work. Description characterizes patterns without making a causal claim. We might compare average income across education groups, describe the association between apartment size and price, or trace inequality over time. Summary statistics, scatter plots, and conditional mean regressions are natural tools. A fitted line tells us how the outcome varies with observed covariates in the data. Unless an identification argument is added, it does not tell us what would happen if a covariate were changed. Prediction aims to forecast outcomes for new observations, hospital demand, apartment prices, or next quarter's output growth. Test mean squared error and cross-validation are the relevant measures. Coefficient interpretation may be irrelevant. Ridge can shrink slopes and lasso can set them to zero while producing excellent forecasts, even though the retained coefficients do not represent structural relationships. A predictive model is judged by honest out-of-sample performance, not by whether every parameter tells a causal story. Causal analysis estimates the effect of changing a treatment on an outcome. Class size, smoking, and policy interventions are examples. The central challenge is selection bias. Treated and untreated units may differ before treatment. Randomized experiments, matching, instrumental variables, difference in differences, and regression discontinuity address that problem in different ways. Low prediction error is not an identification strategy. A causal claim requires a credible counterfactual comparison and a clear target population. The multiple regression model expresses the conditional mean as a linear function of covariates plus an error. Its core assumptions include linearity of that conditional mean, random sampling, conditional mean zero of the error, no perfect multicollinearity, and finite moments. Under those conditions, least squares is unbiased, consistent, and asymptotically normal. Each assumption has a specific role. We should diagnose the one that matters for the question rather than treating them as one indivisible checklist. Add spherical errors, constant conditional variance and no correlation across observations, and the Gauss-Markov theorem says least squares is the best linear unbiased estimator. Best means lowest variance within that class. Linear refers to the estimator as a function of outcomes. Unbiased means its expectation equals the true coefficient. If heterosedasticity or autocorrelation breaks spherical errors, the coefficient can remain unbiased and consistent. Use robust or autocorrelation consistent standard errors rather than replacing the estimator automatically. Different violations have different consequences. A wrong functional form can bias coefficients and calls for transformations or interactions. Endogeneity makes least squares biased and inconsistent and requires a design-based solution. Heterosedasticity and autocorrelation mainly invalidate conventional standard errors. Measurement error can attenuate a slope. Omitting a confounder changes the coefficient. The remedy must match the failure. Robust standard errors do not cure endogeneity, and instrumental variables are unnecessary when only the variance formula is wrong. Exogeneity is the key condition for causal interpretation. After conditioning on the regressors, the error must have mean zero. Omitted confounders, reverse causality, measurement error, and sample selection can violate it. Heteroscedasticity and autocorrelation do not by themselves destroy consistency. Endogeneity does. This distinction prevents a common mistake, reporting robust standard errors around a biased coefficient. Robust covariance estimates uncertainty correctly only around the estimand that the fitted regression actually identifies. An estimator is unbiased if its expected value equals the true parameter for every sample size. Bias is the difference between that expectation and the target. Under exogeneity, least squares is unbiased. This is a finite sample property, but it does not describe dispersion. An unbiased estimator can still be extremely noisy. When comparing procedures, ask both where their sampling distributions are centered and how widely they vary. Consistency is a large sample property. The estimator converges in probability to the true parameter as the sample grows. An estimator can be biased in finite samples, yet consistent, as many maximum likelihood estimators are. It can also be unbiased but inconsistent in unusual cases. Under standard regression conditions, least squares has both properties. Consistency assures us that more data improve accuracy, but it does not guarantee that a realistic sample is already large enough for approximations to be reliable. Consistency matters especially in large observational datasets, where asymptotic reasoning is meaningful. Instrumental variables and generalized method of moments are often consistent without being exactly unbiased in finite samples. In practice, their small sample behavior still depends on design strength, particularly with weak instruments. Least squares remains consistent under exogeneity, even when conditional variance changes with covariates. The point is not that finite sample bias never matters, but that identification and convergence must be separated from efficiency and standard error choice. The first glossary card links several recurring ideas. Aggregation can create an ecological fallacy when group relationships are projected onto individuals. The augmented Dickey-Fuller test treats a unit root as the null. Autocorrelation measures dependence over time. Bandwidth controls the bias-variance trade-off in local methods. Bias is systematic estimation error. A binary variable takes two values, and its regression coefficient compares conditional means. These concepts come from different chapters, but solve distinct empirical problems. The next card moves from probability to design. The central limit theorem supports normal approximations. Compliers are the units whose treatment follows an instrument, and instrumental variables identify their local effect under additional assumptions. A confounder affects treatment and outcome. Consistency concerns convergence with more data. Cross-validation estimates outer sample performance. A directed graph records causal assumptions. Difference in differences subtracts group changes to remove fixed differences and common time shocks. Efficiency compares variances among unbiased estimators. Elasticity measures a percentage response. Endogeneity is correlation between a regressor and the disturbance and destroys ordinary causal interpretation. An estimand is the target quantity. An estimate is its sample value. Exogeneity is conditional mean zero. Fixed effects remove time-invariant unit heterogeneity. Gauss-Markov combines exogeneity with spherical errors to make least squares best linear unbiased. Keeping these definitions separate prevents many vague claims about regression quality. This card connects inference, prediction, and causation. Newey-West errors allow heteroscedasticity and serial correlation. Heteroscedasticity changes conditional variance. Homoscedasticity keeps it constant. A hyperparameter such as lambda or bandwidth is chosen rather than estimated as an ordinary coefficient. An instrument shifts treatment without directly shifting the outcome. The local average treatment effect applies to compliers. Lasso combines prediction with variable selection through an absolute value penalty. A mediator is caused by treatment and lies on the pathway to the outcome, so controlling it changes a total effect into a direct effect. Mean squared error combines bias, variance, and genuine uncertainty. Least squares minimizes residual squares. Omitted variable bias depends on the omitted effect and its relationship with included treatment. Overfitting is good training fit but poor generalization. Parallel trends supports difference in differences. A propensity score summarizes treatment probability for matching. The final card in this group links dynamic and causal ideas. A random walk has a unit root and is non-stationary. Rubin's causal model structures observational treatment comparisons. Regression discontinuity uses a threshold. Regularization penalizes complexity. Residuals are fitted errors. Ridge uses a squared penalty and retains all variables. Spurious regression creates false relationships among non-stationary series. Stationarity stabilizes moments over time. Stable treatment values require no interference and no hidden treatment versions. The regression formula card gathers 4 tools. The matrix least squares expression calculates coefficients when the design has full rank. R squared decomposes total variation into fitted and residual parts. Adjusted R squared penalizes additional parameters. The regression anatomy identity relates the short regression slope to the long regression slope plus the omitted variable's coefficient times its association with the included regressor. It is the algebra behind omitted variable bias. The robust variance formula estimates heteroscedasticity consistent uncertainty. The prediction formulas describe how complexity is assessed. Mean squared error decomposes into squared bias, estimator variance, and genuine uncertainty. Fold cross-validation averages validation errors across held-out groups. Ridge adds a squared coefficient penalty, lasso an absolute value penalty, and the information criterion balances fit against model size. The common principle is to avoid choosing flexibility by training fit alone. Prediction quality must be judged with data that did not determine the fitted specification. The causal formula card pairs each design with its estimand. The average treatment effect compares the 2 population potential outcomes. Difference in differences compares changes. The instrumental variable ratio divides the outcome effect of the instrument by its treatment effect, while 2-stage least squares generalizes that idea. Regression discontinuity measures a jump in the conditional mean at a cutoff. The propensity score is the conditional treatment probability. The equations calculate effects only when their design assumptions are credible. For a descriptive project, define the population and ask whether the sample represents it. Label summaries and figures clearly. Interpret correlation and R squared as descriptions rather than causal evidence. Examine outliers and extreme observations. Beware aggregation bias when group-level patterns are used to infer individual relationships. This checklist may seem simple, but description is not careless analysis. A clear population, measurement scale, and honest statement of what the data show are essential. For prediction, separate training, validation, and test data. Use the test set once at the end. Select hyperparameters with cross-validation, standardize predictors within the folds when regularization requires it, and report test rather than training error. Compare several sensible models and inspect systematic underprediction or overprediction. A production forecast also needs a data pipeline that prevents leakage. The central question is not which algorithm is fashionable, but which workflow estimates future performance honestly. For causal analysis, state the treatment and outcome, draw the causal structure, identify confounders, and avoid controlling mediators. Name the identification strategy and list its assumptions. Run placebo or falsification checks. State whether the estimand is a population average, an effect on the treated, or a local effect for compliers or cutoff units. A pre-analysis plan limits specification searching. If the design cannot identify causation, revise the claim rather than stretching the regression output. The first common mistake is reading correlation as causation. Places with more police may have more crime because high crime areas hire more officers. The direction can run from the outcome to the regressor, and omitted factors may affect both. A least squares coefficient alone does not resolve these alternatives. State the identification strategy. Without one, describe the estimate as an association and explain plausible sources of confounding or reverse causality. Omitted variable bias arises when a relevant confounder is left in the disturbance and is correlated with treatment. Its sign depends on both the confounder's effect on the outcome and its relationship with treatment. Warning signs include large coefficient changes after adding controls, an implausible sign, and strong theoretical reasons for missing common causes. Include measured pretreatment confounders or seek quasi-experimental variation. Adding arbitrary variables is not a substitute for understanding the causal graph. Controlling for a mediator removes part of the causal pathway. If smaller classes lead teachers to provide more individual help, controlling for that help estimates a direct class size effect rather than the total effect. That may be a valid estimand, but it must be intentional. Default control sets should contain pre-treatment common causes, not variables caused by treatment. When timing is uncertain, build the measurement timeline before fitting the regression. Overfitting chooses a model that reproduces training data but generalizes poorly. Data snooping tries many models and reports only significant results, inflating false positives and weakening replication. The remedies reflect the goal. Use cross-validation or test data for prediction and pre-register causal or inferential analyses. Report the specification search, not only the winning result. More computation makes searching easier. It does not make a selected p-value honest. A weak instrument has little predictive power for the endogenous treatment. Two-stage estimates then drift toward ordinary least squares in finite samples, and conventional inference becomes unreliable. Always report the first-stage statistic and use procedures designed for weak instruments when necessary. A large first stage does not establish exclusion or exogeneity, while a small one makes even a valid design uninformative. Instrumental variable credibility requires both causal validity and usable strength. Regressing non-stationary series can produce a highly significant but completely spurious relationship. Two independent random walks illustrate the danger. Plot the series and inspect autocorrelation, run a unit root test, and transform to stationarity or model cointegration when a long-run equilibrium is plausible. A low p-value does not override violated time series assumptions. Temporal persistence can make unrelated paths move together for long stretches by chance. Statistics and machine learning use different vocabulary for overlapping prediction ideas. An outcome becomes a target or label, a regressor becomes a feature, a coefficient becomes a model weight, and residual sum of squares becomes training loss. Lambda is regularization strength, test error is generalization error, and cross-validation keeps the same name. These translations are useful, but they do not erase the distinction between prediction and inference. The objective determines which properties matter. The prediction chapter extends least squares with an honest evaluation split, repeated cross-validation, ridge shrinkage, lasso selection, and regression trees that partition the covariate space. The unifying issue is bias versus variance. A more complex fit can lower training error while raising future error. Feature construction, tuning, and validation are therefore part of the model. The final test sample remains untouched until the entire pipeline has been selected. Prediction methods choose models by forecast performance. Causal methods choose designs by the plausibility of identifying assumptions. Random assignment, parallel trends, exogenous instruments, and local cutoff comparisons create credible treatment variation in different ways. A low test error does not answer a causal question unless the treatment variation itself is interpretable. Regression is the computational tool. Identification comes from the design. This separation is the bridge between the prediction and causal chapters. The diagram shows the book's progression. Foundations establish probability, covariance, correlation, and inference. The regression core develops simple, multiple, and nonlinear specifications. Extensions handle dependence, binary outcomes, prediction, and nonparametric regression. Special settings treat time series and causal analysis. This final chapter synthesizes assumptions, interpretation, and workflow. The sequence is cumulative. Later methods do not replace the earlier regression ideas. They adapt them to new goals and data structures. 7 takeaways summarize the technical core. Least squares estimates a conditional mean and is efficient under Gauss-Markov conditions. Heteroscedasticity calls for robust uncertainty, not automatically a new coefficient estimator. Nonlinearity can be modeled with transformations and interactions. Binary outcomes motivate logistic regression. Prediction needs validation and regularization. Time series require stationarity, dynamic models, and autocorrelation consistent errors. Causation requires a credible design. Regression alone is insufficient. The central message is written plainly. Correlation is not causation. Observational data can still support causal estimates when a valid instrument, a credible policy change, a sharp assignment threshold, or convincing conditional unconfoundedness creates a defensible comparison. The method name never completes the argument. Always ask what generates treatment variation, which assumptions connect that variation to potential outcomes, and whether those assumptions fit the institutional setting. The R software map links tasks to packages. Base functions fit linear and generalized linear models, predict outcomes, and create time series. Other packages provide robust and autocorrelation consistent covariance matrices, joint tests, regularization, instrumental variables, regression discontinuity, unit root testing, clustered estimation, and trees. Do not memorize the list as a catalog. Identify the statistical task first, then use the package that implements the needed estimator and uncertainty calculation. The Python map follows the same structure. Numerical and data libraries prepare observations. Statistical modeling tools fit least squares, logit, autoregressions, integrated time series models, and robust covariance estimates. Machine learning tools provide regularized regression, fold splitting, and trees. A separate package handles instrumental variables, while discontinuity and visualization tools complete the workflow. Reproducibility depends less on language choice than on preserving samples, transformations, seeds, and model specifications. The closing section revisits nonparametric regression because it completes the conditional mean story. Parametric regression chooses a fixed global form. If that form is wrong, bias can remain even in large samples. Non-parametric methods use local observations and impose smoothness rather than one global polynomial. Their main tuning parameter is bandwidth, and their central cost is variance where data are sparse. The following pages reconnect those ideas to the glossary and workflow. Non-parametric regression estimates the conditional mean without fixing one global functional form. At each target value, nearby observations determine the estimate, and bandwidth defines what nearby means. An income emissions curve may bend differently across ranges, making a global polynomial fragile. Local estimation lets the data reveal the shape. This flexibility does not eliminate assumptions. Smoothness, local support, and bandwidth choice replace the fixed functional form commitment. A regression histogram divides the covariate range into bins and averages outcomes within each. It is the simplest local average estimator. Narrow bins use few observations, giving low smoothing bias and high variance. Wide bins pool more data, giving lower variance and greater bias. Hard boundaries create artificial jumps and sensitivity to where bins begin. The method makes the logic visible, but smooth kernel weights usually produce a more stable fitted curve. Kernel regression replaces hard bin membership with weights that decline smoothly with distance. The Nadaraya-Watson estimate is the outcome average under those normalized weights. Each target point has its own weighting pattern, so the curve changes as the target moves. The estimator remains local and interpretable. Nearby outcomes matter most. Its performance depends on bandwidth and on whether enough observations support the target region. Gaussian and Epinechnikov kernels illustrate different weight shapes. Gaussian weights are positive at all distances but decay rapidly. Epinechnikov weights have bounded support. Either gives a smooth curve rather than a staircase. Kernel choice usually matters less than bandwidth, which controls the scale of the neighborhood. Sensitivity analysis should therefore focus first on defensible bandwidth alternatives rather than treating a particular kernel as the decisive modeling choice. Local linear regression improves on a local constant near boundaries. At each target, fit a weighted line using centered covariates. The intercept estimates the conditional mean at the target, while the slope follows the local direction. With observations mainly on one side, the slope corrects the bias of a simple average. The calculation is still weighted least squares, repeated over target points, and it is the default local method at regression discontinuity cutoffs. Local linear fitting reduces boundary bias and adapts to asymmetric data neighborhoods. Higher local polynomial orders can further reduce approximation bias, but they estimate more coefficients and increase variance. Local quadratic may be useful when curvature is clear, yet higher order is not automatically better. At a discontinuity, separate local lines on each side usually provide a more stable estimate than a high-order polynomial fitted across a wide support. Leave one out cross-validation selects a bandwidth for prediction by omitting each observation, predicting it from the rest, and averaging squared errors. Very small bandwidths overfit and give high validation variance. Very large ones oversmooth and create bias. The selected value balances the two. For pointwise inference or a boundary effect, prediction optimal bandwidth may not be ideal because smoothing bias matters differently. State the goal that drove the bandwidth choice. Parametric models are compact, interpretable, and can extrapolate, but they risk misspecification. Nonparametric models learn flexible shapes and avoid one global equation, but their variance is higher, extrapolation is unreliable, and inference is more delicate. A useful strategy is to explore the shape non-parametrically, then use a simple parametric form if it fits that evidence and remains stable under validation. The sample size, dimensionality, and substantive theory should guide the choice. Unconfoundedness says, treatment is independent of potential outcomes after conditioning on observed pre-treatment covariates. The propensity score compresses those covariates into the conditional treatment probability. Overlap is essential. For comparable covariate values, both treated and control observations must exist. Without overlap, a causal effect requires extrapolation rather than comparison. Balanced diagnostics show whether matching succeeded on observed covariates, but unmeasured confounding remains outside what the data can verify. An average treatment effect compresses heterogeneous individual effects into one number. Experiments estimate an average for the study population. Matching or regression adjustment may target effects among comparable or treated units. Instrumental variables identify a local average for compliers whose treatment changes with the instrument. The same numerical estimate can have different policy meaning depending on that population. Always name the units whose treatment variation generated the effect. The last glossary card gathers concepts from prediction, time series, and causation. Time series are ordered and dependent. Training data fit prediction models. Validation data tune them. Treatment effects may vary. Two-stage least squares estimates an instrumental variable model. Unconfoundedness supports observed covariate adjustment. A unit root signals non-stationarity. Weak instruments provide little exogenous variation. The within estimator uses changes inside a unit to remove fixed characteristics. These terms connect the book's separate empirical settings. Use the final discussion to connect concepts across one real example. Classify claims as description, prediction, or causation, and explain why lasso-selected variables cannot automatically be read as causal effects. The goal is to choose methods from the question, not reinterpret results after fitting. This chapter is both synthesis and reference. Description, prediction, and causation require different evidence. Least squares is efficient under standard conditions, but exogeneity is the key to causal interpretation. Unbiasedness and consistency answer different sampling questions. Common failures include omitted confounding, mediators, weak instruments, overfitting, and spurious time series regression. Across modern statistics and machine learning, regression remains foundational. Its meaning comes from the estimand, assumptions, data design, and validation strategy.